purpose of this video is to provide you with some concrete examples of how to find the area of a region enclosed by curves. In this first example, I'm going to give you the graph of the function already developed for you. In the other examples, you'll have to develop this sketch yourself. First thing you do is you look at your graph and you determine on the shaded region what is your top function, what's your bottom function. And then you draw a representative rectangle from the top function to the bottom function. Now remember, this representative rectangle needs to have the exact same function always on top and the exact same function always on bottom for the entire interval in which you are doing the entire shaded region that you're looking at. Next on your graph, you want to make sure you label each of your equations. So here, my top function is the linear equation, so I'm going to label it that negative 1/2 x plus 4. And the bottom function is my quadratic equation, so let's label it the negative 1/2 x squared minus 4x minus 3. Our x equals 4 and x equals negative 1, you may or may not label. That's optional on you, since those are straight vertical or horizontal lines. But you do need to make note of where your shaded region begins and ends. And since our representative rectangle is vertical, we know our shaded region will begin with the smallest x value to the largest x value. Since our representative rectangle is vertical, we are representing respect to x. So the formula we're going to use is the integral from a to b of the top equation minus the bottom equation times dx. So let's look at our example here. We're going to be integrating from negative 4 to negative 1. And our top function is going to be our linear equation, negative 1/2 x plus 4, minus our bottom function, which is going to be the negative 1/2 x squared minus 4x minus 3. Now notice that when I write this, I'm writing my top function in parentheses and my bottom function in parentheses. This is a good habit to get into so that you remember to distribute the negative to all the terms of the bottom function. Let's first clean up our integrand by using some algebra to simplify this expression down. Next, we simply integrate each term, so we get 6x cubed plus 7/4 x squared plus 7x integrated from negative 4 to 1. So we plug in negative 1 to each x into the function, minus plugging in negative 4 in place of each x in the function. Simplifying down, combining like terms, and we end up with our final answer of 21 units squared. For example 2 and 3, when we want to find the area of the region enclosed by the curves, we are not provided with the graph, so that will be our first step. We need to graph each curve. Now, if this problem number 2 had been a problem without a calculator, we need to go back to our knowledge of trigonometry to figure out how to graph 2 secant squared x. Now, if you remember from the beginning of the year, we learned that the cosine function is the reciprocal of the secant function. So we know that secant of x is equal to 1 over cosine of x. If we have the cosine graph memorized, we can use this in our knowledge of inverse trig functions to graph the secant graph. And also notice that the 2 in front, it just changes the amplitude from amplitude of 1 to amplitude of 2. So all we have to do is sketch the graph of 2 cosine of x, and which I will do in dashed lines, and then we will flip that, or do the reciprocal of it, to graph our 2 secant of x. So we know cosine of x goes from 2, 0, 2, 0, 2, and then here we have 0, negative 2, 0, then 2. So this is what 2 cosine of x should look like. Our cosine graph is equal to 0. 1 over 0 is undefined, so I represent this on my graph by drawing vertical asymptotes. And then I reflect the curve of the cosine graph to draw my 2 secant x graph. Squaring a function makes all negatives positive. These 2 curves that I have drawn in the negative will reflect up and now will be positive. So in the blue, this is my final graph. This is what 2 secant squared x should look like, which I'll now put on my actual graph. Knowledge of transformations, I know y equals negative 2 secant squared of x is the exact same graph of y equals 2 secant squared of x, except the negative reflects it on the horizontal axis. So that means my vertices will now be at negative 2 instead of 2, and our U-shaped graphs will be going down instead of up. So here's what my y equals negative 2 secant squared of x graph should look like. Not least, let's graph the lines y equals 0, y equals pi over 4, and the line, and then identify the shaded region that is bounded by all 4 curves, which I will shade here in kind of orange. This was a little messy. I'm going to use this computer-generated graph to look at for the remaining part. So my representative rectangle is now in the form of dx because it's a horizontal rectangle. I plot that on my graph, and I need to set up my intervals of integration for finding the area. Remember, the integrals of integration is top curve minus bottom curve. And this shaded region is bounded from 0 to pi over 4. And my top curve is the positive 2 secant squared of x. And my bottom curve is the negative 2 secant squared of x. We're going to simplify this expression down using some algebra and then integrate in order to find our final answer. So we have the integral from 0 to pi over 4 of 4 secant squared x dx. For integrating this, we can bring out the constant, and we know that the integral of secant squared is tangent of x. Evaluating that at pi over 4, then at 0, we end up with our area of the shaded region is just simply 4 units squared. For our last example, let's start by graphing x equals negative 1, and then let's graph the line x equals 4. And then we're going to graph the two parabolas. I'm going to start with the 1/2 x squared plus x minus 11 halves. Now you can graph parabolas many different ways. For this first method, I'm just going to find coordinates of the points on the curve in between that negative 1 and 4 line. So I'm just plugging in negative 1, 0, 1, 2, 3, and 4 and getting the following points. Once I find the y values, I'm plotting those pairs onto my graph, and I'm going to connect the dots with a line to plot my final curve. For the second parabola, x squared minus 4x minus 1, I'm going to use the vertex method. Remember, you can find the vertex by using the formula opposite of b over 2a. In that case, we get a vertex at 2, and then plugging 2 into our function, we will end up with negative 5. So I know the bottom of this parabola is at the point 2, negative 5, and I know it's the bottom since x squared is positive, the graph is opening up. And then I'm just going to find the y values of my two endpoints, plugging in negative 1 and 4. And then connecting those 3 dots with a curve, and that's going to represent my second parabola. Now I'm going to find the shaded region, but this time I have 2 shaded regions. I have the yellow shaded region and the pink shaded region. So when I set up my integral, I need to find the point where they intersect first so I can figure out my limits of integration. So how I find the points they intersect is I set each of these equations equal to each other, solve, and I find that only 1 is in between the numbers negative 1 and 4. So I know the point in which they intersect has to be at x equals 1, which I already know has a y value of 4. We construct our representative rectangles, and we set up our integrals of integration. So for the yellow shaded region, I'm integrating from x equals negative 1 to x equals 1, because that's when the yellow shaded region begins and ends. And I will use my top equation, which in this case is my blue equation, which is x squared minus 4x minus 1. And I will subtract the bottom function, which is the red equation, or the 1/2 x squared plus x minus 11/2. And now that's the area of the yellow shaded region, but in order to find the area of the shaded region bounded by these curves, I need to add the area of the pink shaded region. And in the pink shaded region, it begins at x equals 1 and it continues on until x equals 4. And we integrate it from our top function, which is the red function this time, minus the bottom function, or our blue function, which is the x squared minus 4x minus 1. Then we want to simplify these equations using algebra, integrate, to find our final solution. So I'm going to speed through the process very quickly. I encourage you to pause this video and make sure you understand where each of these numbers are coming from as I simplify down each expression and integrate each equation. So what I end up with is for the yellow shaded region, I have 13/6 plus 43rd 6, and for the red shaded region, I have 39 thirds plus 13/6, which ends up with an area of 137 over 6 square units as my final answer. I hope this helps explains how to find areas of between curves. Good luck on today's assignment.